classify terms now. A topological diagram, the various inequivalent topological possibilities are determined by the number of external lines or number of external sources and the number of vertices. So if you are given the number of how many sources should be there, how many dots should be there, and how many vertices should be there, then that determines the uniquely the problem of topological classification of the corresponding diagrams. So that's how one should classify the terms in W tilde j and n greater than or equal to 0, T tilde n, where this is a contribution at order j to the power n, which means there are n sources, and each T tilde n can have contributions for many possible values of vertices, number of vertices, and that's given by T tilde n sub v. So this is a contribution at order g to the power v, which means v number of vertices. So let us now study the vacuum diagrams. So we are heading towards a better understanding of the symmetry factors, and more importantly, the 1 over factorial n for n pieces of identical diagrams in a disconnected diagram. That fact has to be checked also in the interacting theory. So that is where we are heading at. So let us begin with vacuum diagrams. These are given by T tilde 0. The first one, T tilde 0 with 0 number of vertices, is of course 1. That is the first term. No j's and no derivatives. That's the 1 in W tilde. That's the first term in W tilde j, which is 1. Then T tilde 0, 1 will be 0. In fact, T tilde 0, any odd number of vertices will be 0. So which means that no vacuum diagram is possible with odd number of vertices. That you can easily check. No vacuum diagram possible with odd number of vertices. No vacuum diagram possible with odd number of vertices because you know, the vertex has only 3 derivatives of 3 links coming out of it, and in order to have a vacuum diagram, you cannot leave any. So every link has to have a paired link. It has to be connected to another link, and therefore total number of links should be even, and odd number of vertices will not provide that. So then let's look at T tilde 0, 2. And that is given by the diagrams this and this. Now, the way to get why I'm writing these 2 diagrams, you can argue that the topological possibilities, you can derive what are the topological possibilities. So you have 2 vertices, and you cannot have any free any free source. So all of them should be linked, and so if you start with 2 vertices, then of course every vertex should be linked. So and the thing is that this is a connected diagram. If you disconnect the diagram, then within a single vertex you cannot you cannot connect all the links, because there are 3 number of vertices. So you have to connect links between 2 vertices, and at least one link should be connected. So let me connect one link, and then for the other 2 links on the 2 sides, there are 2 possibilities. One possibility is that you connect these 2 like this. Each one is getting connected to a link with a in another in the other vertex, belonging to other vertex. And there is another possibility, which is self connection. So this is connected to this, and then self contraction, rather you contract it to this. So these are the 2 possibilities, and these are the 2 diagrams corresponding to this. And mathematical expression can be written down readily for the first diagram. For example, following the Feynman rules, 1 over s, which is a symmetry factor, then there are 2 vertices, so ig square, and then there are 2 integrals, dz1, dz2, the locations of the 2 vertices, and then there are 3 propagators from z1 to z2. So 1 over I delta z1 minus z2 whole cube. That's it. Now, how do I calculate? Let us calculate the symmetry factor. So to get that, let us go back to the term in W tilde j, which is producing this this particular diagram. And since there are 2 vertices, it is 1 over 2 ig over factorial 3 del over I del j cube 1 over factorial. There are 2 vertices, so there are 2 factors of this. And that's going to act on 3 since 2 vertices will have total 6 derivatives for a phi-cube theory, you need 6 j's, and therefore 3 links. So in this, this has to work act on to get these vacuum diagrams. This has to act on this term. Okay. Now you see, let me some more space here. Now the topological variety that we have right here would requires us that each from each factor of this, like 3 derivatives, all these 3 okay, each of these 3 derivatives should go to one of these links. Okay, so this should be distributed like that. Okay, this particular, and from the other j's will be acted upon by these 3 derivatives. So let me color code them. So this one, so let me choose. When you do that, when these derivatives are acting on here, it has a choice whether this one or that one. We will consider that possibilities later, that counting later, but let me just choose one, just one choice. So let me choose the first one, this one here. this one here. This is one possibility. And the other possibility here will be, and these other derivatives will have to go like this. They are going to act on these j's. Now you see this, given this distribution of derivatives, this is only one choice. It could be, you could go, this could go here and this could go here, right? But this is one choice. That's a separate choice. Given this choice, you can notice that these three red lines can be interchanged among themselves without changing the result. So that is a factorial 3 number of possibilities. These interchange among themselves. And that cancels the 1 over factorial 3 factor here. Similarly, among these three blue lines, if you make interchanges, there are factorial 3 number of possibilities that also lead to the same result, and that will counter this factorial 3 down here. So this factorial 3 sitting here actually cancels the repetition of diagrams that are produced by interchanging these derivatives among themselves, right? Similarly, the other thing that we have seen already in the free theory, which is that this factor of 2 is to cancel this the repetitions that you get by interchanging these j's, and so therefore these are all the possibilities. But then the prefactor half and 1 over factorial 3, these are not cancelled by any such repetitions or repetitions of the same contribution, right? So they will remain as a prefactor, and therefore S is given by 1 over factorial 3 times 2. So this suggests an interpretation of various factors in the denominator that we have in this W tilde J. I have written it in a very difficult manner. I have started up from here, so let me go here. And explain it here. So this leads to an interpretation of factors in denominator of various terms in W tilde J, and that is 1 over factorial V I G over factorial 3 times delta I delta cube over V 1 over factorial P half ij 1 over I delta ij to the power P. Let me now color code them. So this factorial 3 cancels. So this is related to this cube. Okay. This 2 is related to the interchange of 2 j's, and this factorial V factorial V is related to this V power and so this cancels repetition due to interchange of V vertices this cancels repetitions due to interchange of propagators. This cancels repetitions due to interchange of endpoints of a single propagator, and this cancels repetition due to interchange of derivatives within the same vertex. Change of derivatives within the same vertex. So in most diagrams, all these four types of interchanges are not mutually exclusive. This means that a set of interchanges has the same effect as the complementary set of interchanges in the same diagram. And these are called matchups. So in most diagrams, all these four types of interchanges are not mutually exclusive. This means that a set of interchanges has the same effect as the complementary set of interchanges in the same diagram. So whenever such a matchup takes place, the corresponding factors in the denominator do not get cancelled. And this gives rise to one over S factor. And such matchups are also related to symmetry properties of the diagram. So we shall next discuss how a few methods of how to calculate from the diagram, how to calculate this directly from the diagram, how to calculate the factor 1 over S instead of going into the detailed expressions in the next part.